This is Griffiths problem 3.16. So problem 3.16 tells us that there is particle A traveling at a certain speed, which hits particle B, which is at rest, and produces particles C1, C2, all the way until Cn. And these are new particles. The problem tells us that we need to calculate the threshold for this reaction in terms of the various particle masses, and luckily the answer is actually given to us as shown below by Griffiths. So the condition for threshold energy, which is what we're trying to find, is such that there is just enough incident energy from the incoming particle to create a number of particles as a result of the collision of particle A into particle B. In this problem, or in the solution to this problem, we're going to use both the lab frame and the center of momentum frame to view this process. And the reason we're doing this is because we're going to use the center of momentum frame to analyze, because it is much simpler kinematically to view this problem as two particles approaching each other at equal speeds, as shown in the bottom picture, rather than as one particle approaching the other, as shown in the top diagram. In the center mass frame, particles A and B approach each other at a certain speed and create a number of new particles that are all at rest. And none of the energy before the collision is converted into kinetic energy, because the threshold energy will only create the new particles and nothing more. So in the center of momentum frame, both the particles hit each other, and then the momentums essentially cancel out, and every new particle that is produced is at rest. All the energy is put into creating the new particles. No energy is wasted as kinetic energy afterwards. And this is impossible in the lab frame because, due to conservation of momentum, if we have one particle colliding into another, there's definitely going to be some residual kinetic energy after the collision, so the new particles will move a little bit. But we're going to use both of these frames to our advantage, and let us proceed now to the energy momentum for vectors. We're going to use energy momentum for vectors to analyze this process. And the reason why is because for vectors are a good choice, since we can take advantage of the invariant dot product. The invariant is a quantity that has the same value in any inertial system. So that means that we can evaluate the invariance in whichever frame is easiest for us, either the lab or the center of momentum frame, and set the invariance evaluated in each of those frames together to solve for whichever unknowns. So essentially we'll have an expression for the invariance in one frame, the invariance in another frame, set them equal to each other, and then solve for whatever value we need. And in this case, we're trying to solve for the energy, the incident energy, which would be the energy of particle A. So let us define P mu total as the total energy momentum for vector in the lab, and P mu total prime as the total energy momentum for vector in the center of momentum frame. In both cases, total energy and momentum are conserved, meaning that it doesn't matter if we evaluate the for vector before or after the collision. The typical energy momentum for vector has the format as shown in the upper left expression. So P mu is equal to E over C, Px, Py, Pz, so E over C, and then momentum in 3 dimensions. So like I said before, it doesn't really matter if we choose to evaluate the energy momentum for vectors before or after the collision in either frame. So say for the lab frame momentum energy for vector, we're going to evaluate it before the collision. So following the format as shown in the expression above the lab frame momentum for vector, we would get this. So as we can see, for the typical energy momentum for vector, it's E over C, and E in our case is replaced by EA plus MBC squared. EA is the energy of the incident particle A colliding with a particle B. So we're just including the rest mass energy of particle B, which is MBC squared. And that expression is divided by C. And since we're dealing with the lab frame, we have a momentum which is only in one dimension. So particle A is traveling in one direction, one dimension. So that can all be summarized as P. Since we wrote down the energy momentum for vector in the lab frame before the collision, we're going to write down the expression for the energy momentum for vector in the center momentum frame after the collision. And again, it doesn't really matter if we choose to write the for vector before or after the collision, because total momentum and total energy are conserved in any frame. So let's go ahead and write the energy momentum 4 vector in the center of momentum frame. So we're following the same format as above, where we have E over C, and in this case, after the collision in the center momentum frame, you just have a bunch of new particles that are all at rest. So E is going to be the rest mass energies of all the new particles. So N is the number of new particles that are created, and M is the mass of each of those, and the C squared from the rest mass energy, one of those C's cancels out with the C on the bottom. So what you end up with if you absorb N and M, small m, into big M, you'll get the expression right here on the right, which is MC000. So big M is the total mass of all the new particles that are created. C is the speed of light. And since we're dealing with the center of momentum frame after the collision, there is no residual kinetic energy, so nothing's moving, and so momentum is 0 in all 3 spatial dimensions. Now we will introduce the invariant dot products. And the invariant dot products are the whole reason why we decided to use 4 vectors to analyze this problem. There's a very powerful property about invariant products, and that is that invariant dot products are the same in any inertial system, meaning that we can actually calculate or evaluate the invariant product for the lab frame, which we did, which we can see on the left side, and we can evaluate the invariant product in the center of momentum frame, which is done on the right side. So we can actually create expressions for both frames and then set them together and solve for the unknown, which in our case, once again, is the energy of particle A. So we evaluate the invariant products as shown below, or shown on the screen, and then we can set them together to create a nice equation which we can rearrange. So in the textbook there's actually a suggestion that tells us that in order to get the energy of a particle when you know its momentum, or vice versa, you can use the standard invariant, which is the expression or the equation shown 3.50 in the text. We can use the standard invariant and we can rearrange it, and then we can sub it back into our expression from before to solve for the incident energy, EA. So we rearrange it, we insert p squared into our previous expression, and then we solve for EA in the following process. So we can see that at this point we have EA is equal to m squared c squared minus ma squared c squared minus mb squared c squared over 2mb, and we're actually done. We solved for the incident energy of particle A, and this expression is actually the same as the one that is shown in the answer given by Griffiths, except that in Griffiths he took out a factor of c squared from all the terms. But aside from that, we are finished.